One of the really important things about doing equilibrium problems, and especially acid-base equilibrium problems, is imagining what is in our solution. So let's think about a solution of vinegar. Vinegar is acetic acid, and acetic acid is CH3COOH, or the Lewis structure looks like this: CH3C double bonded to an OOH. And so if we put vinegar or acetic acid in water, we're going to have a solution that contains acetic acid. So here's the two carbons. Here's the three hydrogens attached to this carbon. Here's the carbon in the middle. Here's an oxygen that's double bonded to that carbon, and here's an oxygen with a hydrogen on it bonded to the carbon. So if we take this acetic acid, it's an acid, and so we know that it's going to act like an acid. So if we represent this as HA, where this part of the molecule is the A part, and the H that's going to get lost is this one right here. That's the acidic hydrogen. So that's the H that is attached to the A. If we think about that, we have HA, which is an acid, and we're going to add it to water. And that's going to be in equilibrium with the conjugate base, A minus, or acetate, this part of the molecule without the hydrogen, and we will have made some H3O+. Now we can see that in our solution we have some acetate. So here's my acetate molecule. It's two carbons. This carbon has three hydrogens on it, and this carbon has two oxygens, but this oxygen has lost its hydrogen. So this is a negative anion. This is acetate. And we have some H3O+ in solution, so here's our H3O+, an oxygen with three hydrogens on it. But we know that acetate is the conjugate base of acetic acid. And so acetate can act as a base. And there's plenty of water around, so it can react with the water to form acetic acid again. And when it does that, the water donates a proton to the acetate, and so the water becomes OH minus because it's lost a proton. And so we should have some OH minus in our solution as well. And in fact, we have right here a molecule of OH minus depicted in our solution. There's lots and lots and lots of water because water is our solvent. And we have acetic acid, we have acetate, we have hydronium, and we have hydroxide. Now we know that water, there's lots of water around, that the water also undergoes autoionization. So two water molecules will react to form H3O+ and OH-. And so we have all of these reactions that are going on in the beaker at the same time. And the question is, which of these reactions is the most important reaction? Which one are we going to think about when we try to solve a particular equilibrium problem that involves a solution which it contains all of these species, all of which can undergo multiple reactions? The way we decide which of these reactions to use to solve our problem is by thinking about which of these species has the largest concentration. If I've added the acid to water, and it's a weak acid, then I'm only going to make a small amount of A-. And so there's not going to be very much A- around. Even though there's a lot of water, there's not going to be very much A- around. And so this reaction is hardly going to go at all. In fact, this weak acid has a weak base as its conjugate base. And so we know that this reaction does not go very far in the direction of products in any case. And if I have very, very small amount of A- in solution, then I can kind of ignore this reaction, or at least I don't need to, it will often be more useful to work the problem based on the species that I have the most of. On the other hand, if I put sodium acetate, so this acetate anion connected to a sodium cation, the sodium acetate is soluble and will dissolve to form acetate anion in solution. And if that's the thing that I put into my solution, then this will be the dominant reaction because I will have mostly acetate and only a very small amount of the acid, acetic acid, because again, this is a weak base, and so this reaction doesn't go very far towards products, so I don't make very much HA. And so that even though this reaction is occurring, it's not occurring to any large extent because I hardly have any HA to begin with. This reaction is always going on, but typically this is not the reaction that we want to think about because we're typically interested in the concentrations of HA and A-, and this reaction doesn't tell us anything about those two reactions. In fact, this reaction is the sum of these two reactions, and so if I think about the acid ionization and the base hydrolysis, I've automatically satisfied this equilibrium reaction by solving the problem based on the acid ionization or the base hydrolysis reaction. The really nice thing about solving acid-base equilibrium problems is that you have a choice of three reactions: the acid ionization, the base hydrolysis, or the autoionization of water. And if you're going to solve an acid-base equilibrium problem, the only three reactions you should be writing are one of these three reactions. So you will always know what reaction to write because it will either be the acid ionization, the base hydrolysis, or the autoionization of water. And those are the only three reactions you need to solve any acid-base equilibrium problem.